Welcome back. We are in part C, right? The third video for this lesson, chapter 2, section 4. And last that we saw each other, basically what I had at the end of that video, I'd given you an example that I said I would tackle the next video, and I even explained that you have a choice if you want to integrate m or if you want to integrate n, but that I would be integrating n with respect to y just because the integration process is easier. Okay, so first things first, hopefully you had a chance to try this. If not, it's okay. But again, let's start to think about the types of questions that are on your first test, right? Or first test or whatever, final, second test, however the structure of the class is. Let's start to think about the tools that you have, and more importantly, the ability to recognize which technique that you're going to use. So again, the directions are just to solve the differential equation. We're just taking a look at this differential equation. We should be leaning towards the using the technique for exact differential equations. But first, we have to test for exactness, right? So if you would have taken the partial with respect to m, and the partial of m with respect to y, and the partial of n with respect to x, you would have found that in either case, you would have gotten e to the x plus x e to the x. So because they're equal, that tells us that we are dealing with an exact differential equation. And so we will use that method for exact differential equations. So I'm going to go ahead and choose to integrate n, which is x e to the x plus 2. All right, I'm going to be integrating that with respect to y. All right, let's go ahead and see what that gives us. So you'll now see why I chose to integrate n. So treating x as a constant, notice that if you have x e to the x, that's just a constant. Likewise, 2 is just a constant. So if you integrate 2 with respect to y, you just get 2y. If you integrate x e to the x with respect to y, what do we get? Well, we get x e to the x y plus 2y. All right, so now because we integrated, remember we have to have that constant of integration. Only when dealing with multivariable functions, as you recall, that the constants themselves are functions. Okay, they're not multivariable functions; they are single variable functions. But they are functions themselves. And in this case, because we integrated with respect to y, the constant of integration would be a function of x. Okay, so are you ready? So how far along are we? So the goal is to find this multivariable function f of x, y. Thus far, we're off to a good start. We have x e to the x y plus 2y plus h of x. Okay, so from here, we need to deal with two different parts. The first part is relatively easy, so let's deal with that first. So what we're going to do is we're going to take, because we integrated with respect to y, we're going to take the derivative or I should say the partial derivative of this with respect to x. Let's go ahead and do that right now. So if you take, obviously if you take the partial of f with respect to x, then that is what you'll get, that the partial of f with respect to x. And of course now we're treating, we're in essence we're treating y as a constant. So let me go ahead and, so we're going to go down the line. We're going to take the derivative of each of these terms. This is a product rule, all right, because you're taking the derivative with respect to x. So you would have to use a product rule. The derivative of 2y, if y is a constant, that's just 0. And of course the derivative of h is just h prime. All right, so what I'm going to do is I'm going to assume that you're okay with being able to do a product rule and go ahead and give you that result. So I'm going to choose a different color here so that you know where this came from. So this, the derivative of this term is going to be e to the xy plus x e to the xy. All right, and then the derivative of 2y is just going to be plus 0. And of course, the derivative of h is just going to be plus h prime of x. All right, so I'm gonna go ahead and drop down here. We have succeeded in taking the partial with respect to x. Just remember that we are allowed to substitute m, right, m of xy, which is what we have right here. We're allowed to substitute that in for the partial of f with respect to x, because that is the definition, right, of we've went through this, of the partial of f with respect to x. So let's go ahead and make that substitution. So what is that going to look like? So now it's going to be 1 plus e to the xy plus x e to the xy equals. All right, so that is the substitution from here. And now let's go ahead and drop everything down. E to the xy plus x e to the xy plus h prime of x. Okay. So at this stage, the goal is to solve for h prime. Okay, so we can see that this e to the xy would cancel this e to the xy. This x e to the xy would cancel this x e to the xy. So quite simply, the only thing you're left with is h prime of x is equal to 1. Okay. Now, remember, let's go back here. This is the setup for the solution. The real thing that we are missing here is h of x. So right now we have h prime of x, but we need h of x. So let's go ahead and do that. So step 5 is going to be integrate h prime of x with respect to x. All right, and that will give us h of x, which is what we want. All right, so h of x is equal to the integral of 1 with respect to x, which is, if you integrate 1 with respect to x, you just get x. We're done. I mean, the only thing that you need to do is make sure you drag and drop this in here, okay? Because when I'm grading these, I'm looking for this, the entirety of this equation, right? It's not my job to find this and then hunt through your work to find this, and then just assume that this is what you want to place here. All right, so I don't have any more space, but the last thing you would do is rewrite this equation with h of x equaling to x. All right, so this will be the last problem of this section. And this is actually a good problem because it leads us into the next section. So as of right now, you know, if you were asked to solve this differential equation, I, as probably as well as you, would just given the setup, I would immediately start thinking that I'm going to be using this method for exact equations. But notice that if you were to try to test for exactness, right? So let's see here. If you were to take that partial of m with respect to y, it would not equal, I don't know what I've written here. Let's try that again. If you're to take the partial of m with respect to y, you would find that as of right now, it does not equal the partial of n with respect to x. In other words, this is not an exact differential equation. And so you cannot use the method that we've been working on throughout this whole section. But wait a minute. What if, right? What if we were to multiply that equation by x? You can tell I'm tired. I've written by by x, but I've continued to write bx. Let me try that one more time. Multiply by x to the negative 1. Let me drink a cup of coffee and just make a loud sip sound while I'm recording a video, just for your ears. Okay, there we go. Okay, ready? So listen. Right now, this is not an exact differential equation, and I'm just suggesting, well, what if we were to multiply by x to the negative 1? Well, maybe you're thinking, well, where did that x to the negative 1 come from? Well, that is the topic of the next section. Well, if you were to multiply this equation, right? If you multiply this equation by x to the power of negative 1, let's see. Let's see what happens here. All right. So we're going to be when I say multiply the equation by x to the negative 1, what I'm saying is we're going to be distributing x to the negative 1 to m. We're going to be distributing it to n. Let's go ahead and just give you the result of that. So after you multiply by x to the negative 1, what is the new m? What is the new n? So now we would have, well, let's see here. So x times x to negative 1 would just be x divided by x. So that's just 1. And then you had 3x cubed sine of y. You would now have plus 3x squared sine of y. For n, you would have x cubed cosine of y. Okay, so now if we retest for exactness, and what you would find, right, if you were to go through, if you were to retest this, you would find that the partial of m with respect to y is equal to 3x squared cosine of y, which is equal to the partial of n with respect to x. So let's pause for just a second, because the rest of this is just things that we've already seen. The topic of the next section is this topic of how to find what we call the special integrating factor, right? So it's a way of being able to manipulate what is currently not an exact equation into an exact equation so that you can solve it using this method, right? In fact, if I recall, the majority of the lectures, the remainder of the lectures in this chapter is all about manipulating equations to get to a form that we know how to solve currently, right? To either be able to manipulate an equation so that you can use, you know, the linear techniques or the exact techniques, or etc. So let me go ahead and finish this very quickly. So what I would, I mean very, very quickly, this is because the rest of this is easy. So what we are going to do in order to solve the differential equation is we would just simply integrate. You just pick which one's the easier one to integrate. I'm just going to integrate m. So that's 1 plus 3x squared sine of y. And since we're going to integrate m, we're going to integrate that with respect to x. And there is that constant. Okay, so let's go ahead and do that integration. So that's easy. If you integrate 1 with respect to x, you just get x. If you integrate 3x squared sine of y, treating y as a constant, you would just get x cubed sine of y. Okay. And now hopefully you know the deal, or you're starting to be able to anticipate the next step. If you integrate it with respect to x, you're going to take the partial with respect to y. So at this stage, we're going to take the partial with respect to y. All right, so what do we get? Well, we're going to get partial of f with respect to y is going to be equal to let's see here, x. Well, okay, so we're integrating with respect to y, so that's as zeros out. And if you integrate sine, my apologies, I'm thinking out loud. We're taking the derivative with respect to y, so that zeroes out. Taking the derivative with respect to y, so derivative of sine is just cosine. Okay, so it's going to be 0 plus x cubed cosine of y plus g prime of y. Okay, so from here we're going to substitute the partial of f with respect to y. We're going to be substituting in for here. So let's write that. X cubed cosine of y is equal to x cubed cosine of y plus g prime of y. All right, so what does g prime equal? It just equals 0. from here we integrate to get to g, and you just end up with g of y is equal to some constant c. Right? So that should make sense if you take the if your derivative is 0, then you must, so think about it. The derivative of a constant is 0, right? So you don't know what that constant is, but the derivative of a constant is 0. So if you're going to integrate, if you integrate 0, you'll get back to a constant. Last thing to do is to simply just take this and plug it back here for g. And that's it. All right, so let's conclude. We'll conclude, we'll go ahead and conclude this section. That's everything I need to tell you. When I see you again, we'll be discussing how do we get this special factor that helps get us to an exact equation. But I will see you in the next video.